All right. Hi, everyone. Sorry for the late start. Acid bases are hard. So welcome. Sorry about Zoom last week. But thanks for coming for tonight. You did your last exam during the semester, so you just have your final left. How exciting. Those grades should be out hopefully like Friday, I think is my guess. So just be on the lookout for that. Other than that, you have a couple weeks and then you're done. How exciting. What would we like to see today? Yeah.
So, when we were doing like the like Q reaction plus Q solution plus Q today.
Yep.
Why were we dividing our like answer by the moles?
Yes, that's a great question. So what week is it?
I know how to get to that part, and I know how to find the moles too. It's just like
Yep. So when we're looking at that stuff there, usually the units that are involved, right, is something where it's like, okay, you have kilojoules per mole, or you have something in kilojoules. So when you're looking at Q is equal to Q cal plus Q surroundings, whatever it actually is, usually this is depending on the units involved. Q comes out to be in kilojoules. The question then asks for what is this in kilojoules per mole? So taking that kilojoules, you're saying, okay, per mole of whatever reactant I have, divide that by the moles, and now per mole of whatever's reacting in the bomb calorimeter is what Q actually becomes. Okay, so right, you have this question where it's
so you're saying answers are usually going to be in kilojoules over moles.
yes.
Okay.
Yep. Right, so this question here, the heat capacity of bomb calorimeter was determined to be 31.5 kilojoules per degree Celsius, and you have a 12.6 gram sample of C2H2 produced a temperature increase of 16.9 degrees. So what is the energy of the combustion of acetylene in kilojoules per mole? Right, so you're going to solve for Q, it's going to come out to be kilojoules. You then need to use the 12.6 grams that you're given to get to moles of that acetylene, and then divide by your answer at the very end to get to moles. Okay, so how would we solve this type of question? Yep, so we have Q is equal to C cal delta T. Yep, so when we have Q is equal to MC delta T, right? MCAT, as most people refer it to. We have M, which is your mass, C, which is your specific heat capacity, and delta T, which is your change in temperature. when we look at Q is equal to MC delta T, there's a mass component of that thing that's changing heat, and you have the specific heat of that thing. So think about when you're trying to heat water, you have a mass of water that you're trying to heat, and that water has a specific heat in order to make the temperature change. Okay, so you have to consider both the mass and the specific heat. kcal here combines the M and the C component already for you, right? Since it's a bomb calorimeter, it's taking in that mass and the specific heat already, and they already did that initial like multiplication step for you.
Would it usually be given like that?
Yes, yep. So, specific heat is joules per gram times degrees Celsius units, right? That's units of C. Units of C-cal are like this guy here, where you have kilojoule over degrees Celsius. You no longer have that gram or that mass component because it was already accounted for. Does that make sense?
Yeah.
Yep.
Then how do we know we can just do like the Q equals C cal times change in T, and then we have to do, or we have to do like the whole equation? I guess, like, is it only doing like the heat capacity of a bomb?
Yeah, so it's like between calorimetry and like bond calorimetry, you can use the C-cal directly. There is a time where it has that extra component with it, but you'll be given more information in the question, I believe, at that point. But like you'll have, when you're given something that's kilojoules per degree Celsius, or it says bomb calorimeter, or combusted in a calorimeter, that would usually indicate a C-cal type of question. Okay. So then we could say that Q was equal to 31.5, right, kilojoules per degree Celsius times delta T. In this case, it was 16.9 degrees Celsius. So you get Q is equal to 532.25 kilojoules. And so how do we get to kilojoules per mole? We need the number of moles, and can we get that from the information given? Yep. We're given, where is it, 12.6 grams. So we have 12.6 grams of C2H2. We can use our molar mass, so 1 mole of C2H2 is 1224, 26 grams. So that's 0.485 moles of C2H2. So then we can take 532.25 divided by 0.485. This is in kilojoules, this is in mole. And then you're left with 1.10 times 10 to the third kilojoules per mole. That makes sense, right? We get the Q just in kilojoules, but it's asked for it in kilojoules per mole. So we need to use that mass component.
Did we not put a negative on the C-cal thing because it's combustion, like we're.
So we don't need. Your temperature is increasing here. So since you're having a positive delta C or a positive delta T, that means that it is absorbing heat. So if it's absorbing heat, it's taking in
Okay.
which makes it a positive
Okay.
heat. Yep. If it's at a temperature decrease of 16.9, then we would want Q to be negative
Okay.
because it's releasing heat. Okay, does that make sense? Yeah, the coffee cup is the one where it's like you have the solution and the you have two of the Q components equal to the reaction. And all of that equals 0. So, right, the bomb calorimeter usually is a little bit more straightforward than a coffee cup. Any other questions?
That's the only two we do classes.
For the most part, I think those are mostly more quiz questions. On the exam and final, you would see more like heat graph questions where you have to do multiple MC delta T or heat diffusion types of stuff. Do you want to practice a little bit of that? Yeah. Okay. Bomb calorimetry or heat graphs? Both. Both. Okay, so right, we remember heat graphs. You haven't done this one yet? Okay. So I'll introduce this to you because you might see it on your homework coming up. Just so you have an easier time, and then we can do a couple practices. So when we look at heat graphs here, or I guess what do they call it? Melting curves. You have this is showing something going through a physical change. So these are all broken up into solid, liquid, and gas. And so anything on a diagonal, you have only one state or only one phase. And on the horizontal lines, this is your either melting or your freezing or your boiling or your condensing. And each component has an equation that you can identify to each part of the graph. Okay, so what this is, and this is temperature. And this is energy. So what you notice is that on your phase changes, you have no change in temperature. You just have all of your energy going towards breaking the intermolecular bonds between those molecules. Right, so for solid to liquid, you're breaking them a little bit so that they have a little bit more free range of motion, right? And then between liquid and gas, you're breaking them so that they can free fly. And there are no, right, ideal gas behavior. There are no intermolecular forces between the molecules. Okay, and that happens at both horizontal lines here. At the diagonals, you're always going to use Q is equal to MC delta T for all three parts of that equation. Or all three parts of that graph. However, the C here is the specific heat. So the C changes depending on the state that you're in. So like, oh, I think C of ice is like 2.08. C of water is 4.18. And then C of gas is like 1.6, something like that. I don't know. Right. But I guess this is vapor. Right, so you have solid, liquid, gas, they all have various specific heats. So you just have to, if you're given a question, you just have to pick which one to use. And then at the horizontal lines, you have Q is equal to M times the delta H of fusion, right? So think about fusing. You're fusing your water molecules into an ice molecule. And at boiling, you have Q is equal to your M times your delta H of vaporization, right? So think vaporizing, you are creating vapor, water vapor, stuff like that. Any questions on the components of a heat curve or melting curve? Okay, and then the other question that they ask with these types of things is that as you go from right or left to right on this graph, right, you're going from solid all the way to gas, is that an endothermic or exothermic reaction? So it would be absorbing. Yep, so it is an endothermic reaction. Right, and if you think about breaking bonds in order to create right, in order to make a solid go from a liquid, all bond breakage requires energy, right? You have, if you want to break the bond between carbon and oxygen, you have to put energy into that. So think intermolecular bonds, you have to break those bonds, you have to absorb energy. So going this way, this is endothermic. So all of your Q's are going to be positive. And if you go this way, this is exothermic as you're forming bonds. So all of your Q's will be negative. That's all we'll really talk about for that one. Just so you don't get super confused. Okay, but that might help you with your homework for this weekend. Okay, so we'll do any other questions, or we just want to practice some things? Practice. All right, so there's a couple questions that we can ask. We'll give you a couple different ones to work on. So This is kind of a hard one. I'm gonna change it a little bit. Mm. Okay. Yeah, let's try this one. So we have determined the final temperature when 18 grams of water at 10 degrees Celsius mixes with 275 grams of water at 60 degrees Celsius. We know the specific heat of water is 4.184 joules per grams times degrees Celsius. Okay, so what kind of question is this one, or what equation do you think we're gonna need? Is this a bomb calorimetry question? Is it a bomb? No, right? In this case, we're just taking two liquids at different temperatures and combining them together. So when you have something like this, or when you have a metal at a certain temperature going into a liquid, you're going to use your Q system, or your Q system is equal to your negative Q surroundings. Right? Q is equal to negative Q. What Q equation are we using for this type of question? Mm-hmm. Yep, so we're gonna use MC delta T for both of these here. Which one is technically going to be the negative Q? Which one's gonna be releasing heat? Which one is you considering your system? Which one are you considering your system in this case?
What is the big Q's up there, the Q,
The 275.
what's the Q's say?
Yep, so Q system minus Q surroundings.
Okay.
Yep, or is equal to negative Q surroundings. So we have our 10, so we have our 18 grams is at 10 degrees Celsius, and our 275 grams is at 60 degrees Celsius. So, say it again.
The 275 be the one for the
Why do you say that?
whole infinite to the
Perfect, right? So our hot one has to get colder and our cold one has to get hotter. So in order to meet in the middle, we have to release heat from the 275 and give that heat to absorb into the 18 one. So if your temperature is going to be less than your starting, then right, your final minus initial would be a negative value. So to preemptively get rid of the negative, you would make your right hand one the 275 because that delta T is going to be negative, where your left hand one or your system would be the one that's only 18 because you're going to have a positive temperature change that way. Okay, does that make sense between the two? So if we were to plug in what we're given from our equation, we know that our mass is 18 grams and we have our specific heat. How do we write delta T? Final minus initial or initial minus final? Final minus initial. Do we know what our T final is? Nope. So we have T final minus, do you know what our initial of our 18 gram one is? It's 10. So then we can do the same thing for the right hand side. We have negative 275. And we have delta T, which is gonna be T final minus 60. So how are we gonna solve for T final? We have to move them both the same side, but that does mean we have to do a little bit of math beforehand as well. So I would probably combine the 18 in the specific heat, and then the 275 on this in the specific heat. And then I would distribute both of those into your temperature change. And then you can move one to the other, right? You have a negative T final, so you can move that to make it positive. And then you can solve for T final by dividing. Let's see if I'm gonna get the wrong answer. Oh.
The 86.652.
Yep.
Wouldn't it? How did it become 800?
Oh, I changed my wrong one. Sorry. I did that for the second one, but not, I did it for the incorrect one there. So we have. I was looking at that and I'm like, I have the wrong, I'm gonna get a decimal on that. I know that's wrong. Okay, yeah, so then that's gonna stay. It should be 652. And that's times 10. I'm just not plugging into my calculator correctly. I think my brain's tired. Okay. One, two, three, four, five. So I got T final is equal to 56.5 degrees Celsius. I think that's right. So we should get 56.5, which if we look at our original question, we have 10 degrees and we have 60 degrees. So we should end up somewhere between 10 and 60, which we do. I was getting a decimal, right? So that should be like red flag. So you should end up somewhere between 10 and 60. You have 275 grams of water compared to 18. So that 275 is going to take a lot longer to either cool or warm up, depending on which way it has to go. So you should end up a little bit closer to that 60 than you do that 10, because you just have so much more of that hot water in comparison to the cold water. So 56.5 makes sense, where the large amount of hot water is not going to cool down too much with only a little bit addition of colder water.
And we just have to know the setup for a question like this is the Q system.
Yes. Yep. Yep. So when this is with two liquids, this could also be something for a metal and a liquid as well.
Okay.
Yep.
Then the negative one is always gonna be associated with basically the one that's like losing energy.
Yes.
Is that
Yep.
right? Okay.
Yep, absolutely. Yep. So anything that's going through a negative temperature change or losing heat, losing temperature is what is going to be releasing heat into the system, or into the surroundings, whatever you want to call it. So that'll always have your negative Q.
So for, the change of speed for the ice, water and vapor, are we gonna be given that or do we know that?
That would be given to you. Yeah. It'll give it to you in the question, or it'll be something on your formula sheet. So then you just have to recognize, right, sea water or sea ice. You would just have to make sure you pick the right one. I've just done this long enough. I know water at this point. I don't think he's released anything in terms of like what would be on the formula sheet, but I know that would be given to you. Like, I don't think he's given you a preview of anything yet. Does that make sense for this type of question? The TF, solving for TF, is your hardest type of problem this way. You could solve for the specific heat, or you can solve for like the mass of the water that you're dropping a metal thing into. And then it's just one variable, it's not on both sides. So those are a little bit easier. But at the end of the day, it does not matter which one you assign the negative number to, or the negative side to, as long as you just keep it consistent throughout the question. Okay.
So would this be considered an exo or endothermic reaction, or do you even have to, or does that even pertain to it?
So you could break that up into both sides. So the cold water is going through what type of reaction? It'll be an endothermic reaction because it's absorbing heat to get hotter. The colder or the hotter water, right, is going through an exothermic reaction because it's releasing heat, right? So when you put ice in your water, or when you put ice in your drink, whatever, your drink is not getting colder, it's actually melting the ice, right? And that's what makes it colder. Right, it's losing heat to the ice. Your ice is getting warmer, which is making your water or whatever you're using colder. Has lack of heat. Did we start talking about like delta H in class yet? Just a little bit.
But that's what they used to describe like endothermic and exothermic.
Yeah.
Like it goes above 0 and less than 0. That's what.
Yes, yep. So, right, we always know that a positive delta H is going to be endothermic. And then a negative delta H is going to be exothermic. Does anyone know what the universe prefers, an endo or exothermic reaction? Exo. So world prefers exothermic. Okay. Okay, we can do a bomb question. I guess we'll do a coffee. We should have done this one in class, but we're going to talk about it a little bit more. So based off of this, we have when 50 mils of 1 molar HCl and 50 mils of 1 molar sodium hydroxide, both at 22 degrees Celsius, are mixed in a coffee cup calorimeter. The temp rises to 28.9 degrees Celsius. If the calorimeter has a heat capacity of 55.8, how much heat is produced by the reaction? Okay, do we know how we're going to solve this one?
reaction was, the Q,
Mm-hmm,
calorimeter?
mm-hmm, calorimeter.
There's another one, I know it's a
Mhm.
Q solution.
Mm-hmm. And what is that gonna equal? Yep, it'll equal 0, right? So all of this stuff together will equal 0 because something is gonna be exothermic, something's gonna be endothermic, right? Heat's gonna be transferred, and at the end of the day, the reaction, the calorimeter, and the solution will all add up to 0. So where do we go to from here?
The Q cal and the Q solution, right?
And how are we gonna solve for both of those? What did we say Q cal was? Yep, we had big C, right? C cal times delta T. And then what is Q solution? Yep, we have delta T, or this would be MC delta T. Okay, so kcal is pretty straightforward, right? Kcal delta T is going to be 55.8 joules over degree Celsius times what's the temperature change? Yep, and how'd you get that? Yep. And then what do we need to do about MC delta T given the information we're given from our question? We need to solve for the mass. And how can we solve for the mass?
Add together Na plus O plus hydrogen means it's just 1 mole, so it's just the mass.
Yep, so we have, right, we have 1 molar, we have 0.05 liters times 1 mole. So we have 0.05 moles of HCl, and then we have 0.05 times 1, which is 0.05 moles of NaOH. So in total, right, we have HCl plus NaOH, which forms NaCl in water. What mass are we solving for? Do you remember what you did in class? You can do it that way. That's one way to do it, depending on the question. I think he wants you to solve for the sodium chloride, if I remember correctly. I might be lying. Right, so if you have 0.50, 0.05 and 0.05. If we have a 1-to-1, how much of the sodium chloride is going to get formed? Mm-hmm. 0.05. So if we have 0.05 moles of does he want you to solve for sodium chloride? Why am I second guessing myself now? Hold on, before I tell you the wrong thing, and totally lead you astray. Yeah, okay. So I actually totally lied to you. You don't need to do any of this. So when you are looking at, you want the mass of the solution, right? And your solution is HCl and NaOH. You know that you have 50 milliliters of this and 50 milliliters of this, so you have a total of 100 milliliters. If you have 100 milliliters, you are making water, you're making a solution, you have a density of 1 gram per mil. So if you have 100 milliliters, how many grams of solution do you have? You have 100 grams. Okay. And right, you're forming water in your solution, so that's why you can say the density is 1. So then we can use our 100 grams up in our MC delta T in order to solve for the Q component of the solution here. So we have 100 grams times 4.184 joules over gram times degrees Celsius, because that's the specific heat of water, again, which would be given to you. And then you did 28.9 minus 22. So your Qcal will equal 385.02. And your Q solution is 288.6.96. So then you can add that up, because then the Q reaction is equal to 385.02, 0.62, 02, yep, plus 288.6.96. And you get Q reaction equal to 327, 1.9698 joules, which is 3.27 kilojoules.
Lower answer not.
So, yep, that's a great question, right? Because we said that. So Q reaction plus Q cal plus Q solution, right, is equal to 0. So this should be Q reaction is equal to negative 3.27 kilojoules. However, we said that our solution raises its temperature from 22 to 28.9. So which one gets the negative sign? Right, the other Q, the Q reaction, ends up having the negative sign, so these will cancel out. Right, the other thing that's going on, the surroundings that's going on, Q reaction, will make it positive. Because we know that because our temperature is increasing, we have to be absorbing heat from something else. Does that make sense? But the Q reaction should be, right, like if we're, what this is doing here is positive. So then if you're like solving for the Q reaction, then you would have the negative there. What's going on just here is positive, but the Q reaction is negative.
So is our reaction always gonna be?
I don't think so, no. Because you could have a scenario where you combine two things and it gets colder. Like a ice pack, right, is a negative or is a positive Q reaction because that is going to be colder at the end. Therefore, right, your reaction, your actual reaction that's happening is releasing or taking in heat instead of releasing heat.
So our final answer is negative?
Our final answer, your final answer in terms of the Q reaction is negative, but what's happening between what's actually going on when you think
Yeah.
about like what's happening in the solution, that's positive.
Okay.
Right, but that makes sense because they should be equal and opposite. Sorry, I lost it. Yeah, thank you. Any other questions? Does that make sense why we used the density of water for the solution? Yes. All right, you were given 50 mils for both of them, so you have a total volume of 100 milliliters after you combine them. Right, and that reaction that happens is the sodium hydroxide and the HCl forming a salt and water, and so you're forming that water solution, and you have 100 mils of that water.
Do you think we need to, have memorized that one, what is it, 1 milliliter is equal to basic 1 gram? Or-
You would be given the density, I believe,
Okay,
if
just
needed,
know.
yeah. Yep, I don't know if that's on your formula sheet, but if it's needed, it would be in the question, or he would put it on the formula sheet.
Good.
Yep. Any other questions for today? No, I know thermodynamics can get hard and all this is crazy. But we don't have another quiz for 2 weeks, so got a little bit of time.
Is the, you know, the final thing, it's cumulative, right?
Your final will be cumulative. It will have a couple more questions based off of the stuff you haven't been tested on yet. So I would say like probably 60% new stuff, 40% old stuff.
Okay, that'll work.
Yep.
Thank you.
Yep, absolutely. And we'll do a bunch of reviews and stuff before that
Okay,
happens. Yeah.
perfect.
Great. Thank y'all.